So in this video, we're going to talk about the graphs of sine and cosine functions. First off, both the sine and cosine functions are periodic functions. And what is a periodic function? A periodic function is a function that repeats its values in regular intervals or periods. So just something that repeats itself regularly. The period of a function is equal to the length it takes for the function to repeat, and the amplitude of a periodic function is 1/2 of the positive difference between the maximum and the minimum values of that function. So from the maximum value to the minimum value, if you take 1/2 of that, that is going to be your amplitude. But we want to make sure that we're always looking at a positive value when it comes to amplitude. So here, the sine function and its properties, it says take the sine values from the unit circle and graph them below. So the first thing that we want to do is plot some of the points that are going to be on our sine function. And the first thing that we need to do is, if we go back to our unit circle, we know that the sine function, when x, or the value that we're plugging into the sine function, is equal to 0, our sine function is also equal to 0. And when the value that we are plugging into the sine function is equal to pi over 2, then our sine function is going to be at the value of 1. And then once we reach the value of pi, now our sine function is going to be at 0 again. So our first part of the sine function from 0 to pi looks something like this. Now, if we keep on going, and don't just stop at pi, but if we go to 3 pi over 2, here 3 pi over 2, or 1/2 pi, now we're going to be at a value of -1. And again, once we're at 2 pi, now we're going to be at a value of 0 again. So it looks something like this. So here's my best sketch of this so far. And obviously, not only does this keep on going, right? It's a periodic function, so it's just going to repeat itself again. And we can also go this way, so it's going to repeat itself again that way. But here, remember that once we go from 0 to 2 pi, we've gone once around the entire circle. And we can definitely fill in different points in between here as well. For example, if we go to pi over 4, try to remember what pi over 4 is equal to. If we go to pi over 4, then what is that equal to? Take a minute, see if you can remember that. Or you can also try to figure out pi over 6, right? Throughout any portion of this right here, you can always just stop the video and see if you can remember these for yourself. Here, this is going to be at square root of 2 over 2. And then this right here is going to be at 1/2. We can go another one in between. This would then be pi over 3, right? That was also a value that we had on our unit circle. And if we go to pi over 3, right here, I'll fill this in, I'll write that one a little bit farther over. This is going to be the square root of 3 over 2, and so on and so forth. We can keep filling these in. Let's fill in, let's see. So then here we had pi over 2. We can also have 2 pi over 3. If we have 2 pi over 3, we're going to end up at that exact same spot for square root of 3 over 2, since these are all symmetric. Here then we can have 3 pi over 4 for 3/4 of a pi, and then 5 pi over 6 until we get to, again, just a pi. So we can keep filling all these in. Obviously, it's going to get a little bit convoluted here if we try to fill in all these other ones. But you can get the idea from this. Obviously, once we get down over here, you can just reverse these numbers into negative values for down here on the negative y-axis, but the concept still remains exactly the same. Now here, if we have y is equal to the sine of x, that's a very, very basic form of using the sine function. But what we can also have is we can have different values or different shifts in our graph here as well. For example, we can multiply the sine by some kind of coefficient, an a value, or we can multiply the we can multiply the x, the value that we're taking the sine of, by some kind of coefficient, or we can add and subtract some value from x, or after we take all of this, right, we can still add something or subtract something from this portion of it right here, and that's what it's referring to as the d. So we have a different way that we can write this, right? One example of this here might be, I'm just going to come up with random numbers now, but we can have 3 times the sine of 4x minus 1, and then we can maybe add, 23 to this. So here I'm just plugging in different values for a, b, c, and d, and again, any of these right here for c and d can just be positive or negative. So we can also have a as being positive and negative, so maybe here should be another plus or minus, and obviously we can also have positive and negative x values or coefficients for those x values. So we can have different forms of that stuff here as well. However, keep in mind, and this is really, really important, that the sine function is an odd function. And we've talked about odd functions before. An odd function is if you take a function and you plug in a negative value into that function, that's the same thing as taking that positive value and plugging that into the f function, but then multiplying the entire function by a negative, right? So again, just to jog our memory about this, an easy odd function is x cubed. Say that we wanted to take x as being negative 1. So then we would have negative 1 quantity cubed for this portion right here. But what is negative 1 cubed equal to? That's just equals to the same thing as taking 1 and cubing it, and then taking the negative of that. These two things are exactly the same. In both of these situations, we get that the value comes out to negative 1. So here what we did was, instead of having the negative sign inside the parentheses and then cubing it, it's the same thing as having the positive value and cubing it, and then just bring the negative sign out front. Again, here where our function f of x we define to be x cubed. We can have all different kinds of odd functions, but here's hopefully a quick, easy example to remind you of exactly what this notation right here means for an odd function. Now, this odd function is symmetric about the origin, right? So here, if you take any value, it's always going to be symmetric about the origin. If you take this value right here, and you go through the origin, you're going to have the exact same value right here. If you have a value right here, and you go through the origin, we're going to have another value over here. So you can think of, that was a little bit off the screen, you can think of the origin as being your mirror, so that's what it means with being symmetric about the origin. The sine function has a period of 2 pi divided by the absolute value of b, and that absolute value of b, the b is the same value that we have in here in this notation for the sine function. And we already know what 2 pi is. And our amplitude is the absolute value of a and again, a being the a from this notation that we have up here. The domain for x is any value that we can plug in for x into our function, and as you can see here, every single value of x that we could possibly plug in is going to be somewhere defined on our function. So therefore, the domain of our function is always going to be from negative infinity to positive infinity. But here, the notation for our range looks a little bit complicated at first, but if we talk our way through it, I think this will make a lot of sense to you. So first off, here is this. This d and the a is again the same a and d that we get from this function up here. This d up here is shifting our graph up or down, right? It's some kind of vertical shift in our graph. So here, this d, if we shift it up by 5, then you can say, okay, we're going to start off our reference point at 5. So here, d minus something, and then d plus something. So it's going to be shifted up by 5. And then we have to subtract the amplitude from it, right? Again, remember that the absolute value of a is the amplitude of it. If we take the shift, the vertical shift, and subtract our amplitude, again, here, this is our amplitude, right? This height right here. Right, because remember that here in this definition for the amplitude, oh, you guys couldn't see that. Here, in the definition for our amplitude, the amplitude is of a periodic function is 1/2 of the positive difference between the maximum and the minimum. Well, here if we have the maximum, and here we have the minimum, then here this is the entire distance between the maximum and the minimum. And therefore the amplitude is 1/2 of the positive difference. So this right here is going to be our amplitude. So from this to this, or 1/2 of it. So this distance from here to here is going to be the same distance as from here down to here. So you can think of this as being the amplitude of our function. So therefore, if we shift our function up by a certain amount, and we subtract our amplitude, and we shift our amplitude up or down, we shift our function up or down and add the amplitude of it, that's going to be the range of our function. Alright, so let's stop talking our way through these definitions. Let's start applying some of these definitions to some examples. And it says, since sine of x is a periodic function with a period of 2 pi, find two other expressions equivalent to sine of the quantity 11 pi over 6. Alright, so we know that it has a period of 2 pi, and we're starting off with sine of 11 pi over 6, and we're trying to figure out two other expressions that are equivalent to this. Well, what we can then do is we can say, alright, if we're starting off with the sine of 11 pi over 6, if it has a period of 2 pi, then we know that this is going to be the same thing as taking the sine of 11 pi over 6 plus 2 pi. And also, if we take the sine of 11 pi over 6 and subtract 2 pi from it. These statements will be equivalent. So let's see why that is true here from a graph. Let's say that here we're starting off at this number, and it's a little bit different than the one that we have in this problem. In this problem it's 11 pi over 6, but just for ease, since our picture is already up here, we'll just say that we're starting off with pi instead. Now, if we go 2 pi to the right, well, here if we go start off with pi, we add 1 pi to it, will be right here. And if we add 2 pi to it, we're going to be over here. So therefore, if we add 2 pi to it, the value is going to be exactly the same thing, right? Here, right, again, remember that f of x is equal to y. So here, when we're looking at the values of the function, we're looking at the y values. And here, when we plug in pi in for x, our y value is equal to 0. And here, if we plugged in 3 pi, or pi plus 2 pi, now our y value would be exactly the same. It would be equal to 0. So what I did here in this problem is I took a value and I added 2 pi to it. So here in this problem I took a value and I added 2 pi to it. And then I also said, well, what I could also do is I could also take that value and subtract 2 pi from it. So the exact same thing would be true. Now this way I'm going over here instead. But here, if I take this value and I subtract pi from it, now I'm at 0. And if I subtract another pi from it, now I'm at negative pi. So here I can subtract 2 pi. And again, the y value here is the exact same as the y value here. It just happens to be 0. Now, what you're probably already noticing is I don't just have to subtract, or there's other options besides subtracting 2 pi or adding 2 pi. You could say, well, isn't the y value in this spot also the same as the y value in this spot? And yes, it absolutely is. And isn't the y value in this spot the same as the y value in this spot? Yes, it absolutely is. So what we could also do in this scenario, if I choose this one, is I could have also added pi to it. But we have to be really, 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 really careful about pi. Just adding pi to it. Because here I simply just chose the value right here of pi. But what happens if I would have taken this spot right here instead? Right? If I would have taken this spot right here instead. Now I'm adding, now my y value is down here. Now if I add pi to it, right, if I go 1 pi farther, I'm going to be right here. But what's the y value for this spot? The y value of this spot is positive up here. So therefore, it just so happens to work out that here, if my y value is equal to 0, that I can add a pi to it. But we have to be careful with the in-between spots. So therefore, the easiest way to do that is, you know that if the period is equal to 2 pi, you know that whatever value that you start off with, if you subtract 2 pi from it and add 2 pi to it, you're always, always, always going to get the same value. There might be other options in between in certain cases, but the surefire way of finding an equivalent expression is to add or subtract the period from it. Right? So here, just to finish up this arithmetic, right? If we take 11 pi over 6 and add 2 pi to it, this is going to be sine of negative pi over, no, I'm sorry, this is going to be, this, it's not going to end up negative, we're adding a positive to it. This right here is going to be 23 pi over 6. And now on this side here, let me try to zoom out a little bit right here. Let me move the camera. All right, now over here on this side, now this is going to be sine of a negative pi over 6. So therefore, if you take this value right here, this value right here, and this value right here, those are going to be identical. For number 2, it says, since sine of x is an odd function, find one other expression equivalent to sine of negative 3 pi over 5. Right, well, remember our definition for an odd function, which we have right here. If we're starting off with sine of negative 3 pi over 5, what the definition of an odd function is saying is we can take this negative sign and simply move it out front. Take this negative sign, move it out front, and these two statements are equivalent. Alright, let's move on to the next page in our notes. And the next page in our notes talks about the cosine function. So a lot of stuff that we're going to do here now for the cosine function is going to be extremely similar to what we just got done doing for the sine function. There's going to be a couple of small, minute changes, but the process and the idea behind these exercises is very similar to what we did for sine. So I might be going through these a little bit quicker, but as always, if you want, you can pause the video or rewind and watch it again. But for the cosine, now if we plug in a value of 0 right here, our cosine value is going to be at 1. And when we're at pi over 2, our cosine value is going to be at 0. And when we are at pi, our cosine value is going to be at -1. Now, when we are at 3 pi over 2, we're going to again be at 0. And lastly, then, when we are at 2 pi, we're going to have a cosine value of 1. And again, we're getting these from the unit circle. So if we connect these dots, my best Picasso of this is going to look something like this. Now, just like we had for the sine function, obviously these just keep on going on and on and on for forever. Or, as Buzz Lightyear likes to say, to infinity and beyond. Yep, even in these videos, I'm still able to get in these puns. Alright, so here, just like we had before, we can fill in some of these things. For, if we go half the distance, pi over 4. I'm going to erase this right here so I give myself a little bit of room for these values. So for pi over 4, we're going to have the square root of 2 over 2. For pi over 6, we're going to be up here. This is going to be the square root of 3 over 2. And for pi over 3, we'll be at 1/2. Now, again, these things are symmetric. So here, if we went to, what would this be? This would be 2 pi over 3. We could follow this over here as well. And then this would just be -1/2. And so on and so forth. So, right? So here, all of these are still going to be symmetric. If you have these additional values over here, you can just have the mirror image of these y values down here instead. Again, you can get these values from our unit circle, but I'll let you fill in the rest of these if you would like, because it starts to get pretty convoluted in this graph. Alright, but now here we have a definitions box just like we did for the sine. We have y is equal to the cosine of x. Again, we can have different values here in our cosine function. We can have different coefficients or add and subtract different values. An important difference between the sine and the cosine function is that the cosine function is an even function. So therefore, instead of taking that negative sign out front, taking f of x is the same thing as taking f of negative x. A really easy example of an even function would be x squared. Again, if we have a negative value, say we have -2 for x, I think all of you will agree that -2 squared is the same thing as taking 2 squared. Both of these situations, it's equal to 4. So it doesn't matter if we have a negative value that we're plugging into our function, or if we're having a positive value that plugs into our function. We have the exact same result. And that is just a quick example of an even function to help you jog your memory. The period of the cosine function is equivalent to the period of that of the sine function. And the amplitude is as well. The domain is the same, and the range is the same. So all of these right here are equivalent. The main difference here, oh, and I skipped this one right here, is since it's an even function, here it's just going to be symmetric about the y-axis. So instead of it being an odd function that's symmetric about the origin, we have an even function that's symmetric about the y-axis. Alright, so I'm hoping that you're seeing the similarities between the cosine function and the sine function in this definitions box, but also some of the things that are slightly different from the sine function. For number 3, it says, since cosine of x is a periodic function with a period of 2 pi, find two other expressions equivalent to the cosine of 9 pi over 10. So just like we did before, if we have the cosine of 9 pi over 10, if we add 2 pi to what we're taking the cosine of, or if we subtract 2 pi from that which we're taking the cosine of, we know that that's going to be equivalent. So again, just like we had before, here we're going to have the cosine of 29 pi. I'll just write out the arithmetic for you. And here it's going to be the cosine of negative 11 pi over 10. So if you take the cosine of this value or the cosine of this value or the cosine of this value, it's going to be the exact same number. Now, like I said before, and I'm going to briefly state again, it is also possible that we could find other values other than subtracting 2 pi or adding 2 pi for certain values. However, the surefire way of always finding equivalent expressions is by adding or subtracting the period of that function, and here the period is 2 pi. For number 4, since cosine of x is an even function, find one other expression equivalent to the cosine of negative 5 pi over 13. Well, again, from our definition of the even function, if we're starting off with the cosine of negative 5 pi over 13, we can simply just drop the negative sign, and we'll end up with the exact same solution. Alright, now for the next problem, we're going to get into slightly different stuff. This is different than what we had before. Number 3 and 4 were very similar to number 1 and 2, but here for number 5, it's going to start asking us to do slightly different stuff. Here it says, determine the amplitude, period, domain, and range for each of the following trigonometric functions. So we have y is equal to 2 over 3 times the cosine of x. Alright, so let's do it. We're asked to find the amplitude, and the period, and the domain, and the range for this function. So let's try to figure it out here. Alright, let's use our handy dandy box that we have up here above. For the amplitude, our definitions box tells us that our amplitude is equal to the absolute value of A, and A is simply just the coefficient that's out in front here. So therefore, the coefficient that's out in front here is 2 divided by 3. So if we want to have the absolute value, and here this is just the same thing as A, the 2 over 3 is the same thing as A. So we're going to take the absolute value of 2 over 3, which is a little bit silly to do, because 2 over 3 is already a positive value, but nevertheless, we'll plug it into our definition above to start getting the hang of this. So therefore, we know that our amplitude is 2 over 3. The period is given to us as, in our definitions box, as 2 pi divided by the absolute value of b, and b being the value that's being multiplied to x. Well, here, there is no value that's being multiplied to x. So what we can have then is 2 pi divided by, you can think of there as being that imaginary 1 times it, right? So here you can imagine this as the absolute value of 1 in the denominator if you absolutely want to have something in here for b in this formula, right? This b, you can imagine as being as this imaginary 1 times x that we just leave away for convention's sake. But if you wanted to plug that in, nevertheless, again, we're just going to end up with the fact that the period is equal to 2 pi. Our domain, right? Domain is always just going to be from negative infinity to positive infinity, so that one is here super simple. And now let's figure out what our range is. Alright, so our range, let me try to scroll up a little bit here but keep everything still visible. Our range, we're going to be using this function, this definition right here. D minus the absolute value of A to D plus the absolute value of A. And then all of this is going to be in our square brackets. So let me put our square brackets right here, and that comma that separates them. We're going to figure out what D is. We're going to subtract the absolute value of A here. We're going to figure out what D is and add the absolute value of A right here. Alright, well here we already know that from our amplitude, the absolute value of A is simply just equal to 2/3. So therefore here, I'm going to plug in 2/3 in here for the absolute value of A into this definitions formula. Now we just need to know what D is equal to, and D is what we're adding or subtracting at the end of all of this, and here we're not adding and subtracting anything from it. So therefore here this is simply just 0. We're not adding or subtracting anything from it. We can imagine as adding and subtracting 0. So now in order to simplify this here, we know that this is then just going to be from negative 2/3 to 2/3. We have our square brackets. Right. Now, again, as always, we're going to go on to the next page in our notes. This would be a fantastic time for you to pause the lecture video and give this next one a chance by yourself, since it's again asking us to find the amplitude, period, domain, and range of these functions. So if you want to pause the lecture video right now, that would be great. I'm going to go through these a little bit more quickly. So here it's asking us to find the amplitude, period, domain, and range. Now if you look at the definition for the amplitude, period, domain, and range for the sine, it's the exact same thing as that for the cosine. So therefore the amplitude is still just going to be the absolute value of our leading coefficient right here, which is the absolute value of -4, and the absolute value of -4 is simply just equal to 4. The period is still just going to be 2 pi divided by the absolute value of b, and b is what we're multiplying to our x in here, so therefore it's going to be the absolute value of 2. Well, here then we're going to get 2 pi divided by 2, and 2 pi divided by 2 is simply just pi. Our domain, as always, is going to be from negative infinity to positive infinity. Remember that these are round brackets, right? I call them round brackets. If you're new to my lecture videos, I call these round brackets, and then when they're square, I call them square brackets. Just the way that I do it. So here these are rounds. I know that they're parentheses, but I'm going to call these the round brackets. And our range always gets the square brackets. Here, what we're going to have is we're going to have D, which is what we're adding and subtracting here. We're not adding and subtracting anything. So therefore we have 0. Here it's going to be minus the absolute value of A. And here we have plus the absolute value of A. We already determined that the absolute value of A is the same thing as our amplitude. So here we're going to have 0 minus 4 and 0 plus 4. Or clearly we're going to go from negative 4 to 4 with the square brackets for our range. Number 7 is really similar again. We're asked to find the amplitude, the period, domain, and range. The amplitude again is going to be the absolute value of A. A is the coefficient that's out front, so here's the absolute value of 3. The absolute value of 3 is simply just 3. Our period is going to be 2 pi divided by the absolute value of B. B is the number that we're multiplying to x in here, so that's going to be equal to negative 5. So we're going to have 2 pi divided by 5, since the absolute value of a negative number is just a positive number. We'll leave it as this. The domain is always going to be from negative infinity to positive infinity, again getting the round brackets. And the range is going to be from, it's going to have square brackets. We're going to take D, which is what we would be adding or subtracting at the end right here, which is again nothing, so we're adding and subtracting nothing. So we'll have D as being equal to 0. Then minus the absolute value of A plus the absolute value of A. And as always, the absolute value of A is our amplitude. So we're going to subtract 3 and add 3 right here. Or simply just from negative 3 to positive 3. Getting the square brackets. The next problems on here are practice problems. And as always, those are left for you. So therefore, that concludes the lecture video for section 6.1.